Hi, it's infuriating exam question time. This one comes from the EEVblog forum. I'll link it in down below if you want to join the discussion, and you should be on the EEVblog forum. This question comes courtesy of Etmel from Sweden. Hi to all my Swedish viewers, and I presume Etmel is doing some sort of course on electronics, and this looks like some sort of exam question. I don't know. I don't think they've put more details in here. Anyway, seems pretty simple. It's got 4 LEDs in here, or LEDs for those who don't like me calling it LEDs. It's just LED. It's easier. Hello. How would I calculate the current at the different points in this circuit? Now, the only information we're given is that VCC equals 4 volts. So we've got a 4 volt rail up here. We've got the forward voltage of the LED is 2 volts at 20 milliamps. So they only give us the forward voltage at the 20 milliamp current, which is very typical for a red LED, and R1 is 100 ohms. So we have to calculate the current through the LED resistor with the resistor dropper here, and then the current in one branch of this circuit here, and the of one of these LEDs in 2 LEDs in parallel, and then the other LED down here. So we've got a series parallel combination string here. Now, the first time you see this, you just go, oh, why on earth are they, like, this is a completely flawed question, and it's infuriating. And if I was, I've had similar actual questions like this in exams, and I don't care if I get well, I would try and get the right answer that they're expecting, but then I would also put a huge diatribe of how this is like complete and utter impractical bullshit. So it's one of these differences between theory and practice, of course. But yeah, it doesn't even make sense, sort of in theory, really. Well, it does, but it's dumb. But anyway, actually, I really think this could be a potentially good question for a job interview candidate. If you're looking for an employee or something like this, throw something, an incredibly simple question like this and see the response. It's for me, a question like this, I would like, rather than just have a multiple choice answer or just have like just tell me the current, I would want like a big description of what's going on here, sort of like explain the issues with this circuit or something like that. So I think this could be a really interesting job interview question, just to see how people respond to it. Do they just go in and blindly try and calculate stuff, or do they put their thinking cap on and go, this doesn't really make sense because XXXX, but I'll still try and answer your question. But like if I got this question in a job interview, I'd immediately want to go to the whiteboard. There's usually often you have your job interviews in a boardroom kind of thing at a company. There's usually a whiteboard in there. Yeah, I'd go to the whiteboard and explain. It's a classic little job interview tip there. If you can, go to the whiteboard, get up, be animated, and start doing stuff. They're so impressed, they'll hire you on the spot. Anyway, so let's look at the issues here. And there are quite a few responses down here, by the way, but I haven't actually read them all yet. But anyway, let's think about this, okay? The first thing is that you never ever put a voltage source, presumably a low impedance voltage source. You have to assume that because it's driving 20 milliamps, it's at least reasonably low impedance, right? You don't put a voltage source directly across a non-linear element like an LED here. It's just ridiculous. So yeah, you wouldn't do that, okay? But we are told that the forward voltage is 2 volts here, okay? So there's 2 volts drop across this one, and there's 2 volts drop across these two in parallel, because they're in parallel, so they'll have the same voltage drop, okay? So this midpoint here is going to be like 2 volts. It's half rail, so it all kind of makes sense. So, you can sort of brush the practical aspect of that away and go, okay, there's 4 volts VCC, and we're going to have 20 milliamps. That means the answer for B here, it must be 20 milliamps, okay? There must be 20 milliamps flowing through B here. But then you engage your brain for 2 seconds and you suddenly realize, well, there's 20 milliamps through here. Kirchoff's current law says that the current entering the nodes must equal the current leaving the nodes. I've done a video on that. I'll link it in up there and down below if you haven't seen that. Kirchoff's current law, and you'd explain this if you're in a job interview and this was an exam question, you go, oh, Kirchoff's current law, right? The current, if you've got 20 milliamps, like coming out of this node here through this lead, which we know, right, is the voltage is going to be split across these, then you must have 10 milliamps each coming through these leads, assuming that they're matched, of course. But here's the problem, like they only tell us 2 volts at 20 milliamps. They only give us the one data point, of course. But of course, a LED is a LED is a non-linear element. So let's just go to a data sheet here. This is literally a universal LED, right? A 5mm universal. Love it. Anyway, this so happens to be, typical voltage, 2 volts. There we go. Forward voltage at 20 milliamps. So this is bang on. It literally is a universal LED, okay? But of course, you go down here, and here's the characteristic curve. Of course, it's non-linear. Forward voltage, sure enough, forward voltage 2 volts at 20 milliamps there. But if you've got 10 milliamps, it's instantly, which we know is in both of those legs, right? Must be, due to assuming they're matched, due to Kirchoff's current laws, then you look at it like 1.8 volts, maybe 1.85 or something like that. Like it's completely screwed up. Anyway, so the answer for C here is, of course, 10 milliamps. And, of course, then the answer for A down here, then you have to do your lead dropper thing. So let's go through that calculation. We know there's 2 volts drop across the LED here, okay? Because that's the only information we're given. So we have to run with that. So that means 4-volt rail minus 2 volts means there must be 2 volts across the 100 ohm resistor. And, of course, 2 volts across 100 ohms is 20 milliamps. A is 20 milliamps, B is 20 milliamps, C must be 10 milliamps. I mean, that's the answers that they're obviously after. But yeah, I would just write a whole, like I'd really go to town. I wouldn't even care if I got this answer wrong, damn it. I would want to give them hell in the comments, So anyway, let's see what some other people here say. It's just a dumb question. It doesn't take practicality into account at all, because LEDs are non-linear devices. That's just like we know this. That's actually information that we're giving. We're actually, even though we're given these figures up here, we are given the schematic symbol for an LED, and we know that every LED is going to have a non-linear response like this. So it just makes no sense. It's dumb. So you could build that up, and I think somebody did down below, and you could see the results, but the results are going to be on the type of LED that you have. Okay, Copernicus says, you don't have to think the exact numbers when you do this. I think that people do too much maths and not enough real thinking when they do electronics. This circuit is so basic, why bother calculating any number at all? But Copernicus is saying, so the right is definitely a lot brighter than the left because it has a resistor in series. But no, there's actually 20 milliamps flowing through this one as well. And of course, the brightness is not a function of the voltage, it's a function of the current. There, diodes are essentially, including LEDs, light emitting diode, it's in the name, is essentially a current-driven device, basically. The voltage drop happens to be a result of driving it at a particular current, but they're not voltage-driven devices. That's not their intention, which is why it's stupid to not have a current limiting resistor or some sort of constant current circuit driving an LED. Don't do it. But then there's people who say, oh, those little keychain flasher things, they put the LED directly across the battery. And, well, batteries have internal resistance, so you do effectively have a series resistance in there. So here comes the tricky bit, right, which not one XOR one picks up. So you would get 20 milliamps through the left branch with the resistor, of course, but he's saying you would get something more than 20 milliamps through the right one, seeing as that there are 2 LEDs in parallel. That means less current and less voltage drop. With real components, etc., you'd get on the left side and larger variations of burnt LEDs on the right. Well, see, here's the thing, right? If you rigidly stick to that, VF 20 milliamps, you'd have 20 milliamps through here, 20 milliamps through here, and then you'd have 40 milliamps Kirchoff's current law must hold, you'd have 40 milliamps flowing through this one down here. But then, like, then the nonlinear nature up here, 40 milliamps, you're up to, 20, 30, 40, right? You're up to like 2.2 volts per lead, which, it's just, no, it's dumb. And Marush here, if I'm pronouncing that correctly. So if we assume an ideal circuit, the LEDs are fully open at 2 volts and the wire has no resistance, then those LEDs would simply blow up because there's nothing to limit current going through them. Well, that's another sort of like theoretical question. It's like, oh God, I hate this question. This is dumb. But here's the point, as Jay Melson points out, the current in the right branch is uncontrolled. Very slight variations in VCC or lead forward voltage will cause huge changes in lead current. That's why all practical lead circuits use a series resistor or a current source. Yes, the current, but as a homework exercise, the current in the right branch cannot be calculated unless you assume the LEDs draw exactly 20 milliamps at 2 volts. It is a pathological circuit and should not even be given as a homework question. It's pathological. Love it. Even with that assumption, it doesn't work unless they assume VS is absolutely constant from 10 to 20 milliamps, which is not. And it's just... AG6QR says the two LEDs in parallel on the top half of the right side must each be getting a portion of the current that goes into the bottom LED on that side, so they can't possibly all three be conducting 20 milliamps at 2 volts. That's the thing. But because this is like a theoretical question, you have to just make the dumbass, impractical assumption that, well, Kirchoff, I would say above everything else, you have to assume that Kirchoff's current law holds. If you're going to learn basic electronics like this, you've probably already, you'd probably have been taught Kirchoff's current law at this point. Well, essentially based on my DC Circuit Fundamentals series, yeah, this would be, it's one of the first things that you actually learn. So, it must hold. And you've been stated that the forward voltage is 2 volts at 20 milliamps. So you have to assume that, look, because these are in parallel, so you have to assume it's just one, right, in terms of like a voltage divider thing. So you have to assume that it's 2 volts, 2 volts. You'll have to assume 2 volts at that midpoint junction there. It's just something that even though it's infuriating, you have to assume that. And once you assume that, and you assume that Kirchoff's current laws hold, you've been told 2 volts at 20 milliamps, therefore the current must evenly split. And because you're making these ideal assumptions, yeah, C up here must be 10 milliamps. But it's infuriating. So I would never write down just the numbers for this answer here. No, rebel against the system. You've got to write down an explanation of why you made various assumptions and things like that. And I would never say somebody is wrong at once. And if they explain why they came up with their reasoning, I would never say that they're actually wrong, unless the answer from their assumptions was actually wrong. But yeah, this is why I think this makes a really good interview question, because it provokes, heated discussion, right? And it shows what the person knows, and it shows that they know Kirchoff's current law. It shows that they're willing to put their thinking cap on and no, this can't be right, and how to analyze the situation. It might be deliberately designed like this. I don't know if the question actually has like a text box, explain your answer, as a lot of questions are. And geez, I'd need a whole page to, I'd really let them have it. Anyway, Xrunner's got it all breadboarded up. Yep, the right side is not acting predictable as suspected because the two LEDs are not identical. Exactly, they're not matched. However, the left side pretty much matches calculations. Yes, it will, because you've got a low impedance current source. Your power supply is a very low impedance output. It's like milliohms, right? It's really small. So it's going to force, unless you've got the current limiter, set, then it's going to force 4 volts to this point. And these diodes on the right-hand side, they've just got to sort themselves out, the poor bastards. But this one over here, nicely designed with this current limiting resistor, then yes, it's going to get the proper 20 milliamp treatment there, assuming you've got the exact lead that, gives you that exact value. But even then, you're going to have temperature and process variations, manufacturing variations over here. This is why over here in the data sheet, look, forward voltage, 20 milliamps, right? It's, can you see that? Yeah, there you go. It's typical of, maximum of 2. Unit 3? Huh? What's wrong with it? Why is that unit 3? What does that mean? Mueller. I don't get that. So here we go. Xrunner's gone to town here. Hats off. Set the input voltage to 4 volts at the breadboard. Measure resistance of R1 was 98.7. Good enough for Australia. Path A measure current was 17 milliamps of VF of 2.14. And you could go in there and trim things and stuff. But yeah, the left-hand side branch doesn't matter because it's going to do its own thing. It's the right-hand path that you're going to worry about. So here we go. Path B current was 10 milliamps. There you go. So it did actually split. And VF of lead B was 2.1 volts. So it did actually share the current because Kirchoff's current law's got to, those leads will sort themselves out. Now here's where it differs in practice. Path B current was 10 milliamps and VF across lead B was 2.1 volts. And if we go up to the top, this is actually 10 milliamps through here at 2.1 volts. So if we've got 2.1 volts across here, we're going to have 1.9 volts left across here like this. So, these things have sorted themselves out and they've determined, they've talked among themselves and going, right, we're going to have 10 milliamps through here. So the current, assuming these leads were from the same batch and reasonably split, so I expect C to be roughly half of that, or 5-ish milliamps. And sure enough, path C was 1.93 volts. The current through each of the leads in parallel was very touchy. I got from 2 to 4 milliamps, depending on the stability of the connection I made with the probes or tapping on the desk. In fact, any slight push on either lead resulted in both lead variations of light output, yet due to slight resistance changes in the breadboard connection. So this is all sorts of stuff that you could talk about in your job interview. If you got given this question or something like that, you can really go to town on the whiteboard, talking about this sort of stuff. In other words, it's very unstable, as was suspected, but that's only because of the physical breadboard and stuff like that. What if you actually soldered them? Yeah, I think you'd actually have to have multiple meters in there. You would have to have 3 different meters in there all measuring that. But suffice to say, and if we had this over here was branch D, if we had a meter there measuring branch D current, C plus D would always equal B, even if they're, changing over time due to the connections or thermal and the leads are just going like this. At any instant in time, the current C plus the current D will equal the current B. Kirchoff's current law must hold. And then Tomoroshki here has gone to town, given the pathological nature of, I love that term, nature of the question. Along with the limited amount of data, we can approach it with a certain ideal conditions. All diodes are exactly the same temperature. All diodes are identical. The ideal diode equation applies, going into the diode equation now. So we're getting into the physics side of things. Look up the various terms there. Yeah, this video is not going to go into details. And I haven't gone through his calculations down here, so I got, I don't know, but yeah, you can treat it sort of more mathematical like this, and it hasn't given a summary like that. So anyway, I'll leave it up. There we go. There's a homework for those playing along at home to give a reply. Go to the forum and give a reply to Tomoroshki. Yeah. Great work. I think everyone is trying to add reality to a homework problem. No issues with the... Well, it's not. You've got to add reality because the question itself is completely dubious. Because it's telling you it's a physical lead, right? It's an LED. It uses the symbol. And that just tells you right away this is a practical circuit problem. And it's just infuriating. So yeah, Arstofa basically comes to the same conclusion I did, that current A is 20 milliamps, current B is 20 milliamps, current C is it must be 10 milliamps due to Kirchoff's current law. No other information was presented. I think the ideal component is all you can use. How you justify the 10 milliamps across the parallel leads? I don't know. And yes, the 10 milliamps is correct. Whether that would actually produce 2 volts isn't given in the problem statement. So yes. So yeah, I put my response down here and then I just went, nah, bugger it, I'm shooting this video. So there you go. One of those stupid theoretical questions. And if you ever see something like this in an exam, let them have it. Damn it, do not stand for these impractical problems in these exams. But of course, it's obvious what answer they're after. But yeah, I really hope a question like this would have a please explain your answer box. I would never, like, seriously, that's a serious fail of a lecturer if they produced this as an exam question and did not give you a please explain your answer box, then that is a failure on their part and you should tell them that. Seriously, might get thrown out, but it's worth it. But I'll say if they did give that please explain your answer box, then hat tip, because this is an interesting one. And as I said, a great job interview question, because it just promotes discussion and you can really extract a lot out of an interviewee if you actually provoke them with a question like this. So anyway, hope you found that interesting. If you did, leave your thoughts and comments down below, and I'll link to the EEVblog forum. If you're not on the EEVblog forum, join in the discussion down below. That's where everyone hangs out, and we can see who's there at the moment. There you go, Xrunner, Amy K, me, RFX, Rstoffer, and there's 7 guests are viewing this topic, probably a lot more after this video. But there you go. I thought I'd share. Thank you very much, Etnol. So Etnol has not actually replied to this yet, but 10 posts, so not a complete newbie. So I assume Etnol will come back and join the discussion. But yeah, please join the discussion in this one. Let us know how you would solve this, and if you think this is an insulting question without having a please explain box, because I think it is. I think this question, yep, it's just, anyway, thoughts and comments down below. Catch you next time. Oh, all right. I know people aren't going to be happy unless they actually build this thing up. So I've actually managed to find, after some searching, 4 red LEDs that are pretty damn bang on to 2 volts at 20 milliamps. And trust me, it wasn't easy to find, but I found them. Anyway, so I'm using my external Keithley current source here. So I've set that to, pretty close to 20 milliamps. It's only 3-digit adjustment, unfortunately, but, that's good enough for Australia, right? 20 milliamps. Let's measure each LED, the voltage drop across each LED at 20 milliamps to make sure they're reasonably matched. And wouldn't you know it, I've actually blown one. I must have hooked it up backwards, and then I thought my compliance voltage was as low as possible, was down at 10 volts, but still, what? Anyway, LED number 1, 1.98. Not too shabby. There you go, it's dropping. She's actually warming up a bit. LED number 2, 1.94 volts. Not matched, but, good enough for Australia. Number 3, 1.99 volts. There you go. Oh, no, 1.98. Right, so anyway, I'm going to use those 3 matched, and this one is died. I don't know if it's a physical failure or whatnot, but look, I'll go find another red LED, and I'll use that in the left-hand circuit, because it's not going to matter. I mean, the whole point is what happens on that right-hand current circuit with the 3 LEDs in series parallel. Look at that, I was able to find another one, 2.02. That's not too shabby, 5mm jobby. Okay, so I've just got the single resistor on the left-hand side of the circuit. So that's our 4 volts input. There you go. And across the resistor, this is bang on 100 ohms, so 1.96. So I know 19.6 milliamps is flowing through there. Ohm's law. Don't even need to get the current meter out for that. So here you go. I'm now going to move it over to put the other LEDs in series. Let's see what happens. I'm going to apply 4 volts. Ta-da! Yep, they all come on. Okay, so I've actually set 50 milliamp current limit on my power supply, and they've all come on. I'll put it right there. Yep, we've still got 4, oh, there we go, 4 volts. Now let's see what we get across the center tap of this string here. Will it be 2 volts? I don't know. Oh, there we go. That's not too, wow, that's pretty close to bang on, isn't it? Interesting, there you go. So let's measure the top one. Of course, we must have 1.98 across there. Well, 1.9. Well, yeah, you can see, yeah, like it's varying a little bit, and that's going to have to do with the Dickey connections on the breadboard. So it's going to be jumping a bit all over the shop there. But as you can see, yeah, we've got 2 volts across there. How much current's actually flowing through down there? Well, we'll have to measure that. Now, of course, burden voltage of your multimeter could get out the microcurrent and stuff. Couldn't be bothered. So what I'll do is I'll just whack it on amps range, and we'll put it on amps jack here, and that will give us a 0.1 milliamps resolution, but really like quite low burden voltage, okay? Yeah, you can see those LEDs flicker when I actually move that resistor in there. I don't, well, I think you can. Yeah, that's just like maybe dirty, crappy contacts on the resistor LED and or breadboard. But anyway, what I'm going to do is put it in there. Ready? I'll turn it on and let's see what we get. 24 milliamps. 25 milliamps, 28, 30? More? There you go. So we are actually getting, in this particular case, we are getting higher current. It's backwards. All the electrons are falling out the wrong way. But there we go. Oh, now it's down to 25. There you go. 26. But it is certainly higher than the other branch. So there you go. That's interesting. Just give that a few wiggles in there just to clean those contacts. This is an old resistor from my junk bin, so, you know, bear with me. Okay, so what I'm going to do now is this resistor. I don't know if it's left or right. Doesn't matter. Take your pick. And there you go. It is half. It's roughly half. We've got our 10 milliamps flowing through the LED. There you go. Winner, winner, chicken dinner. So because these 3 LEDs are all reasonably matched, then they're going to roughly share the current. But of course, that total current through there, you saw that was higher, could be up to 30 milliamps, something like that. But definitely when you put 2 in parallel like this, and they're reasonably matched, then you're going to get a reasonable 50-50 split in the current between there. So, and of course the remainder of the current must be in the other LED. So I don't need to, I could put multiple like meters and stuff, but then you have to like get like, you know, like solder them into proper banana jacks so that you've got, you know, proper cabling and everything set up. And it's, oh, like I couldn't be bothered. That just shows that the current does split between those 2 upper ones, and the combined current, Kirchoff's current law, that one, even though I can't really see any difference in the brightness between these 2 and this. It's not just the camera. It's really hard to actually discern that difference. And this is a thing, even though this has more current, twice the current, as these 2 here, they appear similar apparent brightness to the eye. That's just a trick on the eye. So, you know, there's no need to run LEDs at like 20 milliamps. It's, you could easily half your current there. And if anything, those 2 actually look a bit brighter than that one. Oh, no, it's just because I wasn't looking straight on. But yeah, anyway, yeah, that's just a function of our eyes, really. If you actually got proper measurement instruments that were measuring the millicandelas or the lumens out of this thing, then you'll find that, yeah, the brightness would be proportional to the current, because that's pretty linear. Having said that, diodes and LEDs are non-linear devices. They are in terms of voltage drop, but in terms of output, lumens output per current per milliamp through them, then that's a pretty linear relationship for the most part. So there you go. I hope you enjoyed that bit of pointless fun. If you found it interesting though, give it a thumbs up, and as always, discuss down below. Catch you next time.